Elon Musk recently revealed Tesla Optimus Gen 3, a humanoid robot that is generating great enthusiasm in the technological universe. This is not just a robot capable of walking or dancing, but an intelligent, agile, and extremely capable assistant with accelerated learning skills. Imagine a machine capable of assimilating 1,000 new skills a day using only a Wi-Fi connection and YouTube videos as a source of knowledge. With modern design, advanced artificial intelligence, and a price below $20,000, Optimus promises to transform from domestic routine to whole industrial sectors. What once seemed to have science fiction now quickly approaches reality. Optimus is no longer a distant concept in developing and became an affordable machine, ready to perform complex tasks. The proposal goes beyond providing support. It is about providing autonomy for the elderly, assisting in everyday activities, and even performing educational functions. However, this technological revolution raises deep questions. Are we really prepared to live with machines that can at some point overcome our efficiency and knowledge? The mere mention of humanoid robots causes varied reactions. For some, it represents a future where dangerous or repetitive tasks will be fully automated. For others, it arouses concern, feeding unemployment fears and dystopic scenarios worthy of science fiction films. In the popular imagination, humanoid robots still carry the idea of fragility, clumsy movements, and high cost. The arrival of Optimus Gen 3, however, breaks this perception, offering a functional, robust, and competitive price device. Musk has already stated that the cost of mass production should be between $20,000 and $30,000, making the robot more affordable than a new car. This opens unpublished possibilities for families, companies, and institutions. In particular, the elderly care market can be transformed with an assistant capable of performing everyday tasks, ensuring safety and offering constant and reliable company. The relatively low cost and ease of production are central elements of this strategy. What really draws attention, however, is the learning capacity of Optimus Gen 3. Unlike conventional robots, which depend on manual programming or remote control, this model learns by watching videos and simulating actions in a virtual environment. Just as a person follows tutorials to learn a revenue, Optimus watches the video, practices the task billions of times in the simulation, and then performs it with accuracy in the real world. This is a significant advance in efficiency and versatility. In one of the most recent demonstrations, the robot was seen performing common household chores, sweeping, passing the vacuum cleaner, preparing simple meals, using microwaves, collecting trash, and cleaning surfaces. He was also tested in industrial environments, manipulating pieces in production lines. The great advantage lies in the simplicity of command. A clear voice instruction is sufficient for the robot to understand and perform the task from start to finish, without the need for complex programming. Another important innovation is bimanual coordination. Anterior versions of Optimus mainly used one hand for basic operations. Now, with fluid and synchronized movements, he can perform complex human actions such as handling tools or carrying objects more accurately. This capacity is supported by hardware developed by Tesla herself, with each hand offering 22 degrees of freedom, ensuring delicate manipulation and adaptable to different contexts. Optimus learning is not limited to the individual. Thanks to a centralized intelligence system, whenever a robot acquires a new skill, this information is immediately shared with everyone else. This means that the evolution of a single device translates into progress for the entire fleet, exponentially accelerating the collective capacity of the robot network. This model is inspired by the way Tesla trains its autonomous cars, accumulating data of millions of kilometers driven. Tesla also applies its expertise in electric motors, batteries, power electronics, and structural design in the development of Optimus. The company's large-scale manufacturing experience is a decisive differential, as most existing humanoid robots never exceed the prototype phase or limited production. With mass production capacity, Optimus is no longer an experimental product and becomes a real and scalable solution. In industrial environments, Optimus's shared learning capacity translates into extraordinary productivity gains. Imagine a production line in which, by teaching only one unit how to assemble one piece, all others learn immediately. Quickly, the company would have a catalogue of millions of dominated tasks, ready to be applied in different sectors. In the domestic context, the impact would be equally revolutionary, with robots capable of adapting their performance to each user's specific needs. And it is not just about imitating movements. Tesla's learning model includes a large-scale error correction, ensuring that the final execution of the task is almost perfect. This is especially relevant in sensitive areas such as health, logistics, or high-risk operations, where consistency and safety are essential. Therefore, Musk believes that Optimus can become the most important product in Tesla's history, even surpassing electric cars. The robot is designed to have long durability. While many commercial equipment has a service life between 5 and 10 years, Optimus is designed to operate for up to 24 years under real conditions without major reforms. This resistance results from the choice of advanced materials such as aluminum alloys used in aviation and carbon fiber reinforced polymers, which guarantee robustness without compromising agility. The most critical points, such as joints and column, receive special engineering attention. Internal mechanisms are also developed to resist time. The joints undergo tests that simulate up to 1.5 million complete cycles, representing decades of use. Gears are lubricated with high-quality synthetic compounds, and engines have smart systems to avoid overheating. The energy is provided by Tesla's 4680 batteries, known for its durability and stable performance over the years. Energy management includes adaptive algorithms that avoid frequent overload or complete discharge, prolonging cell life. The robot itself monitors real-time component wear and adjusts its behavior to prevent damage. If a joint is subjected to excessive effort, the system redistributes the load to preserve the integrity of the structure. This self-preservation capacity is one of the most impressive characteristics of the project. In addition, Optimus has a modular architecture, allowing the rapid replacement of parts such as engines, sensors, and actuators without the need to dismantle the entire system. This reduces maintenance costs and keeps the robot functional longer. It also undergoes extreme testing, including temperature variations from 25 degrees C to 50 degrees C, falls, vibrations and dust exposure, ensuring operation even under adverse conditions. This combination of physical resistance, accelerated learning and knowledge sharing puts Optimus in a unique position in the market. Most humanoid robots are still restricted to demonstrations in fairs or laboratories, but Tesla is ready to introduce them into the daily life of people and companies. This paradigm shift has the potential to completely transform whole sectors from manufacturing to service. In an event originally planned to present Cybercab, Tesla's autonomous taxi, the presence of 50 Optimus Gen 3 functional units ended up stealing attention. Visitors were able to interact directly with the robots and witness their abilities closely. It was a striking moment because for many people was the first time a humanoid seemed really useful, reliable, and close to being integrated into everyday life. These units have not only demonstrated ability on housework, but also the ability to perform more specialized functions, such as delivering inspection, serving drinks, and even folding clothes efficiently. The naturalness of its movements and the rapid adaptation to new commands reinforces the impression that Optimus is no longer just a prototype and is becoming an advanced commercial product of development. The target price of $20,000, combined with an estimated production cost of about $10,000 per unit, creates a highly competitive scenario. This is made possible by the use of shared components with Tesla vehicles, such as 4680 batteries and some electronic modules. This standardization not only reduces costs, but also simplifies maintenance and accelerates production. Unlike many competitors who depend on proprietary parts to manufacture, Tesla bets on an integrated ecosystem in which robots and cars share essential technologies. This model ensures scalability and makes it feasible to launch thousands or even millions from Optimus units in the coming years, recalling the revolution promoted by Tesla's own electric cars. Large-scale production capacity also speeds up the rhythm of software evolution. The more robots are in operation in the real world, the more data will be collected and processed, feeding the central network of artificial intelligence. This increases the learning curve and diversifies the skills of each unit, either in the kitchen of a residence, in the assembly line, or in the halls of a hospital. In the health sector, for example, the integration of Optimus could open new possibilities. With accuracy and continuous learning, the robot could assist nurses in tasks such as drug transport, patient monitoring, and equipment hygiene. This would allow human professionals to focus on functions that require clinical judgment, empathy, and complex decision-making, increasing the efficiency of medical services. In the logistics sector, the presence of humanoids, such as Optimus, could also transform workflows. Imagine distribution centers where robots move freely through the corridors, collecting and packing products while communicating with each other, and management systems to optimize delivery routes and deadlines. This complete automation not only increases convenience, but also reduces costs and minimizes errors. Even in education, there is a vast field of applications. An Optimus could act as a personal tutor, assisting children in learning languages, mathematics, or programming in an interactive and personalized way. With instant access to adaptive databases and teaching methods, each robot could adjust the content and pace according to the student profile, making learning more efficient and motivating. Still, the impact on the labor market generates inevitable debates. Replacing human functions with machines causes resistance and concern, especially in sectors where automation advances rapidly. Musk and Tesla argue that, as in other technological revolutions, new types of jobs will emerge to take advantage of the opportunities created by these robots, partially compensating for the loss of traditional positions. From an ethical point of view, important questions arise. To what extent is it safe to allow highly autonomous machines to operate in human environments without constant supervision? How to prevent programming failures or sensors from provoking accidents? Tesla states that its experience with autonomous vehicles serves as the basis for developing redundant systems and robust safety protocols, minimizing risks.